Welcome, learners. In this video, we will talk about error handling in Solidity as an advanced topic. Solidity has many functions for error handling, and the errors can occur at compile time and runtime. Solidity is compiled to bytecode, and there a syntax error check happens at compile time, while runtime errors are difficult to catch and occurs mainly while executing the contracts. Some of the runtime errors are out of gas error, data type overflow error, divided by zero error, array out of index error, and so on. Until version 4.10, a single through statement was there in Solidity to handle errors. So, to handle errors, multiple if-else statements, one has to implement for checking the values and through errors which consume more gas. After version 4.10, a new error handling construct assert, require, revert statements were introduced and the through was made absolute. Let's dive deeper into the error handling mechanisms in Solidity. The first one, require statements. The require statement is used to validate conditions before executing the transactions. It's commonly used for input validation and enforcing preconditions. If the condition specified in the require statements evaluates to false, so the transaction is reverted with an error message. This helps prevent invalid states or operations. Following are some cases where require type of exception is triggered. When require is called with the arguments, which result as false. When a function called by a message doesn't end properly. When a contract is created using the new keyword and the process doesn't end properly. When codeless contract is targeted to an external function. All of these statements are require statements. This Solidity code demonstrates the usage of require statement to validate inputs and conditions within a contract. Let's break it down. At the first, Pragma Solidity, this specifies the version of the Solidity compiler to use. About the contract definitions here, defines the require statement contract. Then we have a function, check input. This function takes an unsigned integer input as input and checks if it falls within the range of uint8, I means 0 to 255. It uses two require statements. So the first require statement check if input is greater than or equal to 0, ensuring it's valid uint8. Okay, invalid uint8. The second require statement checks if input is less than or equal to 255, ensuring it's valid uint8. If either condition fails, the transaction is reverted with the respective error message. Otherwise, it returns input is uint8. Function odd. This function checks if an input is odd. It uses a require statement to ensure that input is not equal 0, meaning that the reminder of dividing input by 2 is not 0, indicating that is an odd number. If the condition fails, okay, the transaction is reverted. Otherwise, it returns true. So in summary, the require statement is used in Solidity to validate inputs and conditions within a contract. If the condition is specified in the require statement evaluates to false, then the transaction is reverted with an error message, providing a way to enforce preconditions and prevent invalid operations. Now we have assert statement. The assert statement is similar to require, but is typically used to check internal invariants and conditions that should always be true. Unlike require, which is used for user inputs and conditions that might fail due to external factors. So assert is used for conditions that indicate internal errors or bugs in the contract logic. If an assert condition evaluates to false, then the transaction is reverted unconditionally. So this is the assert. Let's see this example. The assert statement used to check the condition and ensure it's true. Let's break down this code. The first line about Pragma specifies the version of the Solidity compiler to use. Contract definitions here means contract is defined. About the state variable, result is a Boolean state variable declared within the contract. About the function check overflow, this function takes two unsigned integer parameters, num1 and num2, as you see here. Okay, it calculates their sum and assigns it to sum. Then it uses assert to check if the sum is less than or equal to 255. If the condition is not met, okay, so the contract execution will halt and any remaining gas will be refunded, okay? About the function getResult, this function is a getter function that retrieves the result of the assert statement. If result is true, it returns no overflow, okay? Otherwise, it returns overflow exists. So in summary here, the assert statement in Solidity is used to ensure certain conditions are true during a contract execution. If an assert statement evaluates to false, it indicates a critical error in the contract logic and halt execution to prevent further incorrect behavior. Now we have a revert. Revert statement is a fundamental error handling mechanism in Solidity. It's used to revert the current transaction effectively, undoing any state changes made. Okay, reverting the Ethereum virtual machine to its previous state. So revert often used for conditions that should never occur, indicating critical errors or unexpected states. For instance, if an invariant is violated or if an operation leads to an inconsistent state. In this Solidity code example, the revert statement is used to revert state changes and halt execution if a certain condition is met. So let's break down the code here. Pragma, as we said previously, specifies the version of the Solidity compiler to use. Then we have defines the revert statement contract. Function check overflow. This function takes two unsigned integers parameter, num1 and num2, calculate their sum and assign it to sum. Then it check if the sum is less than 0 or greater than 255. If this condition is true, it executes revert overflow exists, which halts execution and reverses any changes made so far, while providing an error message, overflow exists. If the condition is false, then it returns no overflow along with the sum. So revert statement in Solidity is used to revert state changes and halt execution if certain conditions are met. It's often used to handle exceptional conditions or to ensure that certain requirements are met before proceeding with execution. Let's go to talk about custom error. Custom errors allows you to define custom errors using the error keyword, okay? So custom errors provide a structured way to handle exceptional conditions within your contracts. You can actually define custom error types with specific parameters, allowing you to provide additional context when reverting transactions. This is especially useful for providing detailed error messages or information about the cause of the errors. In this example, some amount is deposited to the owner address, and if owner wants to transfer this amount to give an address, then first we check withdraw amount is less than owner address amount. If the condition is matched, then withdraw amount is successfully transferred to the given address. Otherwise, if the condition is not matched, then transaction is reverted with the help of error statement provided by the contract. So this Solidity code demonstrates usage of SPDX license identifier, as well as the comments here in this code. So this line indicates the license. Then here the version of the Solidity about Pragma. Then here we have comments. Contract custom errors. This is the defines of custom error contract. State variable. Here we have BAL's mapping that associate each address with a balance. Okay. We have a function. This function allows user to deposit funds into their account. It increases the balance associated with the caller addresses by the value sent with the transaction. We have here also custom error statement or definition, lack of funds, okay, error defined with parameters withdraw AMT and available AMT. Okay, this custom error is used to handle cases where the withdraw amount exceeds the available balance. We have here also function checks custom error. This function allows user to withdraw funds from their account and transfer them to another address. So before transferring funds, it checks if the caller's balance is sufficient to cover the withdraw amounts or not. If not, it reverts the transaction using the custom error, lack of funds, or providing details about withdraw amounts and the available balance. Otherwise, it deducts withdraw amount from the caller balance and adds it to the receiver's balance. So in summary, this Solidity contract demonstrates the usage of this license and the definition of custom errors to handle exceptional conditions during contracts execution. Actually, there is another mechanism, which is gas consumption. It's essential to consider gas consumption when handling error in Solidity. Reverting transactions consumes gas, and excessive use of revert statements can lead to higher transaction costs. Therefore, it's important to design your error handling logic efficiently and minimize unnecessary gas consumption. This involves carefully considering where to use require, assert, or custom errors based on the specific conditions and the requirements of your contracts. So each of these error handling mechanisms serves a distinct purpose and should be used in appropriate way depending on the context and the requirements of your smart contract. By leveraging these mechanisms effectively, you can ensure the security, reliability, and efficiency of your Solidity contracts. Thank you for watching.